All right. So if you can hear, the recording has just started, and we'll go ahead and get started with our meetup. We are so delighted to have Emily Zabor speak for Our Ladies Philly. So if you aren't familiar with Our Ladies is a worldwide organization that promotes gender diversity in the R community via meetups and mentorship in a friendly and safe environment. And gender diversity includes, but is not limited to, cis trans women, trans men, non binary, genderqueer, and agender. And we're so happy to have all of you join this meetup today. So, if this is your first Our Ladies Philly meetup, welcome. You can learn about our future meetups at our meetup page. You can join our Slack community by emailing philly@ourladies.org. You can subscribe to our YouTube channel where we will post this recording, and we would love to have you volunteer as a speaker, a mentor, or an organizer. I'm going to let Emily introduce herself.
Great. Hi, everyone. I'm Emily Zabor. I'm here in Cleveland, Ohio, where I work at the Cleveland Clinic as a biostatistician, a cancer biostatistician. I'm based in the Department of Quantitative Health Sciences and also the Taussig Cancer Institute here. And primarily, I work with doctors on their research projects doing applied biostatistics. That's my main area of focus, but I also do some statistical methods research and clinical trial design, retrospective data analysis methods. And I love R. I use a lot of R. Programming is a big part of my daily job. And I'm a big fan of Our Ladies too. I used to be involved in the New York City chapter when I was there before I moved to Cleveland, and I'm happy to be here today.
And you want to put a plug in for Our Medicine?
Yes, I would love to. I'm also chairing the organizing committee for the Our Medicine conference this year, which will be taking place June 10th through 13th. It's a fully virtual conference with lots of a wide variety of topics. It has 2 days of workshops and demos where you can learn in depth about different packages and techniques, and then 2 days of keynote speakers and talks. And so please, if you have an idea for a talk, you should submit your abstract. We actually are happy to even work with people who want to be new speakers to help you, think about what goes into your slides. All the talks are pre-recorded, so it's a great opportunity to try out speaking if you haven't done it before. And otherwise, please attend.
Awesome. So we'll let you go ahead and get started with the main content for today. I'll drop the links in the chat. And if you have questions during the course of the tutorial, then you're welcome to drop those in the chat and I will speak up and relay those to Emily.
So I'm going to share my screen, just find the right page. Oh, gosh, that did not mean to do that. 1 second. Okay. Great. So full screen. Today, I will be talking to you to introduce some survival analysis techniques in R. And I already introduced myself, so I'll skip that part, but just wanted to mention that this talk is based on a larger tutorial that you can find on my website. The link is here, and Shannon's going to drop the links to both the full tutorial and also these slides into the chat. They can all be found on my website, but it's kind of a funny thing that despite the work that I actually do in most of my time, I think the thing I'm best known for is this survival analysis and R tutorial. So I originally developed it for an internal training back in 2018 when I was working as a biostatistician at Memorial Sloan Kettering Cancer Center. And I've kind of kept it up to date a little bit since then. And I'm happy to talk to you about the first part of it today. It's what you'll find in the full tutorial as part one, just some kind of introduction to survival analysis and the basics of doing it. And if you check out the full tutorial, you'll find some more advanced topics there that we won't have time to cover today. So what are survival data anyway? Survival data are data that have distinct start and end times. So some examples from oncology are a start time might be the date of diagnosis, the date of surgery, or the date of treatment start, and an end time might be the date of death or a date of disease progression or recurrence. And so, for example, some other examples from cancer include like the time from diagnosis to death, or the time from surgery to the recurrence of a disease, the time from the start of a treatment to progression of disease, or the time from a response to treatment to the recurrence of a disease. But survival analyses are done in many other fields, both healthcare fields and other fields. And I've just listed some other examples of when this might come up in other fields, like the time from production to a machine malfunction, or the time from an HIV infection to the development of AIDS. And because survival analysis is common across a lot of different fields, not just healthcare, where survival analysis is probably the main name that it goes by, it has a number of other names that you might hear about this type of analysis, including reliability analysis, duration analysis, event history analysis, or simply time to event analysis. And I go a little bit back and forth between using survival analysis and time to event analysis sometimes, but there are quite a few other names that you might hear of this, depending on what field you work in. So one of the main features of survival data is censoring. And censoring occurs when the event that we're interested in is not observed after a certain period of follow-up. So I'll show you some examples of this in a couple of slides, but you might think, these endpoints, death, recurrence, aren't these just binary data, right? You either die or you don't die. But binary data doesn't have the ability to change depending on the time of analysis. So for example, if we were interested in 5-year survival, it would have the same value, whether it's analyzed at 5 years and 1 day, 5 years and 2 days, 6 years, because we just care if you were dead or alive at 5 years after follow-up started. You either died by then or you didn't. But time to event data can have different values depending on when you do the analysis or when you obtain the data. So for example, if we're interested in something like overall survival, it would have different values depending on whether it's analyzed at 5 years and 1 day or 6 years, since additional participants would die between those two times. So I mentioned censoring, and specifically today I'm going to be talking about right censoring, which is a type of censoring that occurs when the event occurs beyond to the right of the time that we're analyzing the data. So in this plot, we have a time in years on the x-axis and just some example data for 10 subjects plotted on the y-axis. And we can see that a yellow triangle denotes an event and a green circle denotes a censoring. So some patients are followed and they have the event or they're censored before the time of analysis, which is denoted by the blue dashed line. And some have an event or a censoring after the time of analysis, but we don't know what that information is after the blue dashed line. So this is right censoring, where it occurs to the right of the time of analysis, you can think of it. So some reasons for censoring are that a subject may be censored due to loss to follow-up. Maybe, for example, I work at a hospital, and if someone moves away from the area and they continue their treatment or their follow-up somewhere else, we won't know anymore what's happened to them. If you're talking about a clinical trial or a more formal study, they might withdraw for various reasons, or it simply might be that they just have not had the event by the end of a fixed study period. So if we follow patients for 3 years, some of them just might have been followed that whole time, but they haven't had the recurrence or death by the end of that time period. So I mentioned right censoring, and I'm just going to briefly mention that there are a number of other types of censoring. Two main ones that I encounter in healthcare data is left censoring, which is when the event or censoring occurred before a study started or before data was collected. So those patients never even make it into your data set. And interval censoring, which is when the event or censoring occurred between two dates, but we don't know exactly when. And that type of censoring is actually very common in cancer studies where something like disease recurrence is only detected by imaging. So we can only say that you had the recurrence at a date when an imaging test was done, but the actual recurrence must have occurred sometime between a prior negative imaging time and a positive imaging time. But today I'm only going to be talking about right censoring. Just be aware that there are other types, and it's important to think carefully about this. So just coming back to this plot, I'm going to go through a little example of what is here and what components of data we have. So we need to consider the censoring when we do the analysis. So for example, think about how would we compute the proportion of patients who are event-free at 15 years? So if we go back, we can see that subjects 7, 8, and 10 had the event before 15 years. So that's these 3 subjects. We see that subjects 1 and 9 were censored before 15 years. So that's these 2. And then the remaining subjects were event-free and still being followed at the time of analysis, 15 years, which is denoted by this line. So these patients, we don't know anything beyond this. So how would we determine the proportion who are event-free at 15 years when 4 of our subjects, we don't know what has happened to them? And also, how would you compute something like median time to event when the event time is unknown for some patients because it hasn't been observed yet? So these are some of the questions that we're going to try and answer with survival analyses. Some additional reasons that survival analysis are needed is that the distribution of follow-up times is skewed. So traditional methods that rely on normality to look at distributions of data are not appropriate in this case. So you can see here, this is just a plot of a distribution of days of follow-up, a frequency plot. And we see that the blue distribution is in blue. The censored patients are shown in blue and the patients who have died are shown in yellow. Because another problem that can occur with this type of data is that the distribution may differ between censored and patients who had the event. And so in that case, it's not appropriate to use, traditional summary statistics. So I'm not going to dwell on any mathematical notation in this talk, though I've included some here, but I'm going to just go through everything kind of with words and descriptions, but there's 2 main components that we need for a survival analysis, which is the observed time, which is the time that we have observed the patient, and the event indicator, which denotes whether or not the event has occurred at the end of follow-up. So the observed time is just the minimum of the event time and the censoring time, so whichever comes first. And the event indicator is just a 1 if the event is observed and 0 if censored. And I will actually talk about the 1 and 0 a little bit more when we get into the R components. So just some packages that you would need to go through this, and I'll introduce specific packages that are more customized to survival analysis, but I'll just note here that dplyr and ggplot2 are just common packages I'm using for like data cleaning and plotting purposes. And I won't go into any details about those, but I will discuss the other 4 packages as I come to them. So I'm going to use an example data set today that's different from what is on the main tutorial page. This is an example data set that I have created and I have available on a GitHub repository, so you can install it from there. It's a simulated data set that is kind of simulates a cancer study that I've worked on before. So just some code here to install this data set and load it. And just to describe what it is, the data set is named BCRT data, and it's a synthetic data set based on a real breast cancer study. It contains information on 3,000 women with early stage breast cancer who had a mastectomy between certain years. And the original study of the true data was looking at the association between the use of post-mastectomy radiation therapy and disease recurrence. And if you're interested in the study, I've included a citation. But the relevant data that we're going to be using today include a variable called RT, which is an indicator of whether or not the patient received post-mastectomy radiation therapy. It's 1 if they received it and 0 otherwise. OS_event is the event indicator of whether or not they died, a 1 if they died and a 0 if they were censored. And then the 2 dates we need to calculate the follow-up time are the date of mastectomy and then the date of last follow-up or death. So that single variable contains the date of last follow-up for patients who were censored or the date of death for patients who died. So just showing you what the data look like by looking at these few variables, you'll see we're just looking at the first 10 patients here, this indicator of the radiation therapy, the event indicator, and then these dates of mastectomy and last follow-up, which we can notice here are currently formatted as character variables in the data. And in my experience, that's the most common way that I get data is to be formatted as a character in an Excel data sheet or something. So a few things that are important to pay attention to are, the first is the event indicator. Some of the code that I'll be showing you to use to do the survival analyses require certain formats for this variable, the event indicator. And the one that I have in the data set, example data set, where 1 is the event and 0 is censored, is one of the accepted formats. You can also use true or false, where true would be the event or false would be censored. Or you can have a 2-1 variable, where 2 is the event and 1 is censored. I find this to be very confusing, so it's important to pay careful attention because I definitely have received data sets before where 1 is an event and 2 is censored, and you would have to switch that before you could analyze it using the functions that I'm going to introduce. But in this case, we already have the right format, but this is just something important to pay attention to. So the other important component is the start and end dates. And as I mentioned, these are currently formatted as character variables. So we'll need to do two things. The first is convert them to date format. And the second is to calculate the follow-up times. So I don't know if many of you have worked with dates before in R, but it can be challenging. And in my experience, the lubridate package is a great way to work with dates. It's my preferred way of working with dates. I think it offers a more comprehensive and user-friendly suite of functions for date manipulation compared to what's available in base R. And I find it a little bit easier to use. And there's great documentation on the lubridate website, which I have linked to here. So I'll just show you an example of how we would use this. We saw previously that the dates were character format with the numeric month and a backslash, the numeric date, a backslash, and the numeric year. So we can use the MDY function from the lubridate package to convert the character value to be a date, an actual date format in R that R will recognize as a date. So then we can perform calculations on it. Because the reason we need to do this is you can't calculate a time difference between two character variables. They won't be recognized as being related to any type of calendar value. So we just do this. I'm just going to keep the same variable names and use the MDY function to convert those character variables to dates. So just taking a look at the first 10 patients again, now we see we have the same indicator for PMRT, indicator for the event, and now our dates look slightly different. This is how we usually will see a date printed in R. We see the format here is shown as date, and now we can see the 4-digit year, the 2-digit numeric month, and the 2-digit day. And so these we can now do manipulations on. So what we want to do is calculate the follow-up time, which is the amount of time between the, in this case, the date of surgery, the date of mastectomy, to the date of last follow-up or death. And the lubridate package includes this special operator that's a % with 2 dashes in between and another % sign. I have no idea what you would call that operator. I've never referred to it as anything. And this is a special operator that can create an interval from a specific instant to another instant. And I'm saying instant instead of date here because it can include time components and other details, which I haven't really used it for before, so can't go into the details of that. But it'll actually knows how many days are in a month, if it's a leap year or not, and things like that. So it can calculate a proper amount of time between two dates. And then we're going to divide that by D years 1, which is just a conversion of the interval to be on the years scale. The interval itself will be between two numbers that are pegged to like some date, maybe the 1st of January, 1970 or something like that. I don't remember what it is, but it's some specific date, and the number has no meaning to me whatsoever. So you need to convert it to be on years. And so what we have here is the date of mastectomy, our little special operator to create the interval from that to the date of last follow-up, and then we divide by the D years to get back years. And just a note here that actually this variable is already in the example data set. I just wanted to demonstrate how to create it yourself because that's an important part of working with survival data. Okay, so it's important to check the follow-up times once you've calculated them because in real-world data, it's very common to encounter errors in data, such as end dates that come before start dates. So you'll end up with negative follow-up times or things like this. So just some of the quick checks that I usually do are to look at the numeric and visual distributions of the follow-up times. So usually just a quick summary of these years, we see they go from just above zero, which is good. That means some, patients had a short amount of follow-up time, but it's still positive, which is required. If you see a negative here, you definitely need to look into some of your dates because negative follow-up time is not possible. And we see that some patients were followed all the way up to 21 years with a median of 6.3. And just taking a look at the histogram, and it looks like what I would expect with positively skewed distributions that are all positive. So now I'm going to get into some of the coding, and we'll be using a few different packages for this, but the survival package is the main package that forms the basis of the survival ecosystem in R. It began development in 1985 as part of the software program, and then was converted into R. It has over 11 million downloads with active development ongoing. And the main author of the survival package does provide many detailed vignettes that cover both basic and advanced topics. So it's a good place to look for help, and all of the essential methods that you need for a survival analysis are really available in this package. It's the backbone of any survival analysis. But we'll be using some complementary packages as well in this tutorial. The first is the GT summary package, which creates a number of highly customizable tables, and I'll show how to use it today for a couple of different things, but a few applications to survival analysis include the table survfit function, which can create tables of median survival time and tables of X time event-free probability, which I'll introduce in a little bit. And then also the table regression function can nicely print out your tables of univariable or multivariable Cox regression results. And I'll introduce all of those methods in a little bit. And the last package we'll be using as a complement to survival is the ggsurvfit package, which uses ggplot2 as the basis. So all of the known customizations, if you're familiar with ggplot2, are available using the plus sign operator with this package, which is kind of a nice feature, whereas the base R, the plotting that comes with the survival package uses base R plotting. So if you're used to ggplot2, it's a little harder to customize those plots. So I'll be showing you how to plot Kaplan-Meier curves using the ggsurvfit function and some of the options available. So in my opinion, all three of these packages used together is really where you're going to find your best combination of things to use in R. Okay, so first we need to learn about the survival objects, which is created through the surv_S function from the survival package. It creates a survival object that will be used as the response in formulas to create plots and to do regression analyses later. So in the output of this, there will be one value for each subject, which is their survival time. And then it's followed by a plus if the subject was censored, and followed by nothing if they weren't. So you can see here, if we just print it out for the first 10 subjects, 9 of them were censored at various times. You can see the plus, and then this one had an event at this time 5.5. So you don't really need to ever look at what comes out of this, but it's an important part of creating other survival analyses. So first we're going to look at some Kaplan-Meier plots, and the Kaplan-Meier method is the most common way to estimate survival times and probabilities. It's a non-parametric approach that results in a step function where there's a step down each time an event occurs in your data set. So the way we create a survival curve is using the survfit function from the survival package, and it creates it based on a formula. So here's our survfit function. And then what we have on the left hand, this is our formula. So you can see the tilde for the formula. And the left-hand side of the formula is the surv object that I mentioned. And what goes into surv is your time variable. This is our time variable that we calculated that measures the amount of the number of years between the date of mastectomy and the date of last follow-up or death. And then your event indicator is the second thing inside the parentheses for surv. So this is the left-hand side of our formula, and that's what creates that component that I showed you. That's just the time followed by either a plus or no plus. And in this case, we want to look at the curves overall. So there's just a 1 on the right side of the formula. We're not going to be stratifying these curves at first by any variable. And then you just need to supply your data set. So some key components that come out of this object are the time, which is the time points at which the curve has a step. So that means any time where at least one event occurred, that would be in the time component. And then serve, which is the survival probability estimate at the corresponding time. So at every time where at least one event occurred, there will be a survival probability estimate and the time. So to create the Kaplan-Meier curves with ggsurfit, we actually want to use a minor alternative to the surfit function that's included in ggsurfit, and it's called surfit2. And it's kind of you don't need to worry too much about why you want to do this, but essentially it tracks the environment from the function call, which allows the plot to just have better default values for labeling and p-value reporting. So it takes the whole environment, and so if you have labeled variables or something, it can use them directly on the plot by default. But you can absolutely use ggsurfit with the regular surfit function. It's just a nicer outcome if you don't. So exact same code, but now we just have a little 2 on the back of surfit too. Okay, so here's how we might make a simple survival plot with ggsurfit. So this S2 is this object, surfit2 object I created here. I have my serve on the left-hand side and my 1. And now I'm going to pass that into ggsurfit. And then I'm just going to customize a few things. One is the labels. And I'll talk a little bit more about this in a minute, but I'm going to label the x-axis as years from mastectomy and the y-axis as overall survival probability. The default says the default says time on the x-axis and just, I think, probability on the y-axis. Then it's very important to always make your y-axis go from 0 to 1. Unfortunately, by default, that's not how the plot comes out. And so sometimes if you have a plot that is way up in the top part of the plot like this, it might start at 0.5 or 0.25. And it can be a little misleading when you first look at a survival plot if you don't have the full probability scale on the y-axis, in my opinion. So I think this is an important thing to always change. And then I'm just changing the x-axis limits, which I'll talk about a little bit more too, to go from 0 to 15 and to have breaks every 5 years, just to customize that. We can also add confidence intervals to this, and we just do that by adding on the add confidence interval, which provides this gray shaded area. And then we can also add the risk table, which is this numbers at risk that's at the bottom of the plot, by adding on the add risk table. And here I'm just saying risk table stats is n.risk because I only want to see the number at risk, not the number of events. And by default, it shows the number at risk and also the number of events at each of the times. And it will print this at the times corresponding to where you have tick marks on your x-axis. So because I specified that my x-axis goes from 0 to 15 with breaks every 5 years, we can see we get the numbers at risk at each of those times. And it's always kind of nice to look at this to make sure you have your expected sample size in here at time 0. If you don't, that's a good indication that there's maybe something going on that you're not aware of. And then, you should see these numbers will be going down over time as events occur and patients are censored. So this is a Kaplan-Meier curve. And some common mistakes that I see with these curves is plotting the y-axis on a scale besides 0 to 1. I actually get asked to do this a lot by doctors I work with who want to zoom in on a plot that's pretty high up. And usually what I'll do in that case is to put like an inset plot where we zoom in, but it's inside the plot that's on the big scale. So when you first look at it, you can really see, the survival probabilities are very high up, close to 1. Plotting the x-axis beyond the limit of reasonable confidence. And what I mean by that is that at a certain point, we won't have any patients left in our data set, perhaps, and that you can't get a good estimate of a survival probability when there's no patients at risk. And so that's why you'll want to cut the x-axis at a certain point, and a rule of thumb is not to go below 5 or 10 events. It kind of depends on the size of your data set. There's no hard and fast rule, but what you'll see, I'll just back up here, is as time goes on, our confidence intervals are getting wider and wider and wider. And that's because we have less and less certainty about these probabilities as our sample size of patients at risk decreases. And so, I cut this off when there were 6 patients at risk, but arguably you might even want to do that beforehand because this is a pretty unstable estimate with a wide confidence interval at this point. So it's good to start out looking at the full plot and then decide on a reasonable place to truncate that x-axis. Another common mistake is adding too much extra information to the plot face. Like you'll see in papers, people put in tables of hazard ratios, which actually don't have anything to do with a Kaplan-Meier plot. They're from a completely different method. Or adding p-values, median survival times, and all of this extra information that kind of makes it hard to just look at the plot and take in the information. Another common mistake is using default or non-descriptive axis labels. Like I mentioned, the default is for the x-axis label to say time. There's no way for there to really be a better default because your time variable is generic to the functions, and so they don't know what you're measuring. But it's important to say something more descriptive, like here I've said this is years from mastectomy. So it's not just time. Time from what? If you just say time, you don't really know what the zero time point is. Here we know that is 0. This is when the patients had the mastectomy, and we're going forward in time. And the last thing is ignoring negative or missing survival time. So sometimes if you have not paid close attention and checked your time variables, you'll see that you either have missing values, maybe because a follow-up date was formatted incorrectly in the data set and it read into R as a missing value, or just a variety of data checking issues can lead to you having negative or missing survival times that you need to go back and check and make sure you have all of those positive times with correct dates entered. So those are just some things to pay attention to. A few other things we might want to do after creating a plot is to estimate X time survival. So here X is just being used generically to represent a point in time. It might be 1 year or 2 years or 5 years. And it's commonly of interest to want to estimate the probability of surviving beyond that point in time. So for example, in this data set, say we want to estimate the probability of surviving to 10 years. We can use the summary function just around our survfit object. So this is what we already had. It was named S1 before, but I'm just including it here for demonstration purposes. If we just wrap that with summary, and then supply 10 to the times argument of summary, what we get back is this object that shows at time 10, we still have 386 patients at risk. There have been 501 events. This is our survival probability, which is 0.727, which is 72.7%, the standard error, and it gives you also the lower and upper bounds of the confidence interval at that time point. So what does X time survival mean? The 10-year survival probability is the point on the y-axis that corresponds to 10 years on the x-axis of the survival curve. So if we were to find this time point 10 and come up to our curve and then draw over to the y-axis, this is our point in time that represents the probability of surviving beyond 10 years in this data set. And a common mistake with X time survival is to use a naive estimate. So a naive estimate would be something like, we know that 501 of the 3,000 patients in the data died by 10 years, and a naive estimate might be calculated as 1 minus 501 over 3,000. So this is the proportion of patients who died. We subtract it from 1 to get the proportion who are still alive, multiply it by 100 to get a percentage, and we would find 83%. And this would be a way where we're calculating it based on the numbers without any consideration of the amount of follow-up time. And you get an incorrect estimate of the 10-year probability of survival because here you're ignoring the fact that 2,113 patients were censored before 10 years. So they were not followed all the way up to that 10-year mark, and they really cannot be considered to have contributed data that whole time. And recall that the correct estimate was 73%. So this is quite an overestimate of the 10-year survival. And just to illustrate that with a plot, you will always have overestimation to some extent. Sometimes it might be minor and sometimes it might be more major, like in this case, when you use a naive estimate. And that's because censored subjects only contribute information for a portion of the follow-up time, and then they fall out of the risk set. And so they actually pull down the cumulative probability of survival. And so ignoring these censored patients erroneously treats them as part of the risk set for the entire follow-up period. And so you can see here in this plot, in the yellow curve, we have the true curve that includes the censoring. And in the blue curve, if we ignore the censoring, you get a greater and greater overestimation over time as patients are censored over time. So we can also make nice tables of the X time survival probability. You saw the output from the summary function gave you all the information you needed, but how do we extract that and put it into a report or present it in a paper? And we can do that using the table surfit function from the GT summary package. So this code on the left shows that we just take our surfit object, which is here, which we've seen before, and we pass it, we pipe it into table surfit. And here we're going to say use the argument times equals 10. And then I'm just going to adjust the label of the results column to read 10-year survival, 95% CI. And what we get back is this table for overall survival. And it shows that we have the 10-year survival of 73% with the confidence interval. So this is just a nice way to present those results. Another common quantity that we might want to estimate in a survival analysis is the average survival time, which we usually quantify using the median. And the reason a median is of interest instead of a mean is because survival times are not normally distributed. As I pointed out earlier, they have a positive skew, and so any type of mean would not be an appropriate summary. So we can, again, obtain the median survival directly from the survfit object. So here I'm just printing out this survfit object. If you print it out, it actually will give you the median survival. So here it's just showing, we had 3,000 patients, a total of 526 events. And what we see here is the median, and then the lower bound of the confidence interval and the upper bound of the 95% confidence interval. And in this case, what we find is that the median survival time is showing as NA, which means that it has not yet been reached in this study. And this is actually common in scenarios where the event rate is low or follow-up time is short. And I'll show you what I mean by that. So the median survival is the time on the x-axis that corresponds to a survival probability of 0.5 on the y-axis. So we do something similar as when we were looking at the x time survival. Only now we start on the y-axis at 0.5, and we draw our line across until we hit the survival curve, and then you would go down to the x-axis. But in this case, you see we draw our line all the way across the whole follow-up period, and the curve has not crossed that 0.5 line. So that's what we mean by the median survival has not been reached, which means that half of the patients have not had the event of interest in this particular data set. So in median survival, a common mistake is similar to that of X-year survival, which is using a naive estimate. And by naive here, I mean summarizing the median survival time among patients who had the event. So say we take the 526 patients who did die, and we just do a straight median estimate of their follow-up time, of their survival time. And we would find that that comes out to 4.79, which is an incorrect estimate of the median survival time, because recall that the correct estimate is that the median survival time was not reached in this study. And just to illustrate that again, you will always get an underestimate of the median survival when you ignore censoring. And that's because the follow-up time that censored patients contribute is ignored completely. And so the risk set is artificially small. And so you see in this plot, when we consider the censoring, this is our original Kaplan-Meier survival curve. And when we ignore it, we're ignoring all of those patients who were censored, and we see that we're only looking at events in the patients who have them, and our survival probabilities are much smaller, and that's what leads to this estimate of just under 5 years for the median. And again, we can get a table of median survival using the table surfit function from the GT summary package. And the syntax is very similar to what we saw to get the X-year table, only instead of saying times equals 10 here, we're going to say probs equals 0.5. And you can do this for any probability. So if you're interested in other quartiles of the survival distribution, you can get it this way. I've never done that myself. I've only ever been interested in the median. And you can see that this table is completely uninformative in this example because the median survival time wasn't reached. It will just give you dashes, but if you had reached the median survival, the numbers would be displayed in this table. And I used this example data set on purpose because this median survival time not being reached is actually somewhat common, and it's an important thing to be aware of that it can occur in think about how to present that. And typically when this happens, we would report this as just NR or not reached in a report. Another thing of interest in a survival analysis is to compare the times between groups. So we can conduct between group significance tests using a log rank test, which equally weights the observations over the entire follow-up time. There are also versions of the test that more heavily weight either early or late parts of the follow-up that might be more appropriate depending on the research question. I won't go into details here, but if you look at the help page for the servdiff function, you can see some of the different test options there. So to conduct the log rank test, we can use the servdiff function, which is from the survival package. And so say, for example, we're interested in whether there's a difference in survival time according to our post-mastectomy radiation therapy variable, which was in this RT variable. So we just have our survival object on the left, and now we have our RT variable on the right and our data set indicated here, and we put that all inside of the servdiff. Oh gosh. Sorry. I don't know actually what I just clicked that made that happen. Sorry about that. So we just put that all inside our servdiff function, and here's what you get back, which is not the easiest thing to look at, but what you will find here is the p-value down in the bottom right corner of the output, and we can see that in this case, we get a significant difference in overall survival according to post-mastectomy radiation therapy with a p-value of less than 0.001 here. So this is a small p-value. We can also add this log rank p-value to our Kaplan-Meier curve. So just by doing a plus sign and saying add underscore p-value using the ggsurfit package. So now we have our Kaplan-Meier curves according to radiation therapy. So you see the blue line is patients without radiation therapy, and the yellow line is patients who received post-mastectomy radiation therapy. So now we also have two rows in our table of at-risk numbers, one for those who received radiation and one for those who didn't. And our p-value has been added here to show there's a significant difference between these two curves. So we can see that the radiation therapy patients have a higher overall survival probability than those who did not receive radiation therapy.
Do you think some subjects in
Yeah.
this data set are missing the radiation therapy? Would I expect those at-risk numbers to be 3,000?
Yeah, I don't think anyone's missing it, so I'm not actually sure. That's
Okay.
a really good question. It should be 3,000. Actually, no. In the synthetic data set, there are patients who are missing it. Sorry.
Okay.
In the original data, no one was missing it, but in the synthetic data I created, there is like artificial missing data included for other
Got it.
purposes, and some of them are missing that. That's a good question. I should have pointed that out. You're a fast adder too to notice that.
All I do
All
is
right.
count things.
Yeah. I just have a few more slides and there will be some time for questions at the end, if anyone has them. But this is the last topic, which is the Cox regression model. This is a very common approach to quantify an effect size for a single variable, or if you want to include more than one variable into a regression model to account for the effects of multiple variables. So the Cox regression model is what's called a semi-parametric model. It can be used to fit univariate or multivariable regression models. And the things that are of interest are that we're interested in the hazard, which is the instantaneous rate at which an event occurs. So Cox regression has some assumptions that could be important for you to check. One of them is non-informative censoring. And what that means is that the reason that patients are censored in your data set is not related to the variable that you're investigating. So for example, if you're looking at the radiation therapy, like in our example, you might imagine a scenario where if radiation therapy is hard to tolerate, patients might drop out of your study and become censored earlier. And in that case, that would be informative censoring, where there is an association between the variable of interest and the rate of censoring. So we do have to assume non-informative censoring in order to use this method. There are ways to account for it, but it's not built in. So the other one is proportional hazards, which just means that the difference between any two groups is the same over time. It stays proportional over time. So not getting bigger or smaller over time. And I'll just note here that parametric regression models for survival outcomes are also common, but I don't cover them at all in the current version of the tutorial. So the effect estimate we're interested when we do a Cox regression model is called a hazard ratio. And a hazard ratio represents the instantaneous rate of occurrence of the event of interest in those who are still at risk for the event between the two groups. So if you have a regression parameter beta, which we don't need to worry about notation, then the way we get a hazard ratio is by exponentiating it. And I'm just showing this because this comes up in the R code. So a hazard ratio less than 1 indicates a reduced hazard of the event, whereas a hazard ratio greater than 1 indicates an increased hazard of the event. And we'll go back to our example to take a look at this in more specific context. We can fit regression models using the Cox-PH function from the survival package. So it's very similar notation as doing a Kaplan-Meier curve where we have the serve object on the left-hand side, our tilde for our formula, and then our variable of interest in the regression model on the right. So here I'm just including the radiation therapy variable. If you wanted to fit a multivariable model, you would just include additional variables with plus signs after this. So I'm saving this Cox pH fit to this object mod1. And on the next slide, we'll see that we can create tables of the results using the table regression function from the GT summary package. And we need to set the option exponentiate equals true to get hazard ratios. Otherwise, it'll just print the regression coefficients, which typically aren't of specific interest because they're not as interpretable. So we just pass our oh my gosh, I did it again. I actually had no idea why that happens, that when I click on that little, like, I'm so sorry. Now I
All
know not
good.
to click anything. I have never experienced that before, that clicking on like a piece of code would take me
Yeah,
back to my starting slide. Is that a known feature?
I haven't experienced that either, but I'll play around with it.
Yeah. Now I know. So this is like showing us like a little link or something. Anyhow, sorry about that. So we're back here. You just pass your object mod1, which is the Cox pH fit, into table regression, exp equals true, and I'm just labeling my variable, which would show as RT. That's the name of the variable, to show as PMRT in my table. So we get this table back here, which shows PMRT as a characteristic. Our hazard ratio is 0.72, 95% confidence interval from 0.6 to 0.86, and a p-value of less than 0.001. So this implies that receipt of post-mastectomy radiation therapy is associated with 0.72 times the hazard of death as compared to no post-mastectomy radiation therapy. So this is our measure of the effect size. So just note a few common mistakes with Cox regression. One is overfitting, which occurs when there are too few events to support the number of included variables. So a rule of thumb is to have 10 to 15 events per degree of freedom, but you can kind of see how your model is doing by the width of the confidence intervals, whether you have any convergence issues. And this can be a problem even in a very small data set. I work in rare diseases sometimes, or data sets where patients are doing quite well, so there aren't as many events. You might have issues even including a single variable in a Cox regression model. Another common mistake is to interpret a hazard as a risk. They're related ideas, but they're not the same. So I'll often see people just say, as I mentioned on this previous slide, we have a 0.72 times the hazard of death. You'll see often this described as 0.72 times the risk of death. It might seem like a minor point, but it really doesn't have quite the same interpretation. And it's important in statistics to be precise. And another is overlooking the proportional hazards assumption. And if you go to the main tutorial page that you have the link to, there's a section on how to check that assumption if you're ever in this context. But you will not get necessarily interpretable results if the proportional hazards assumption is violated. And that was the end of the material I have to cover today. So I'm just leaving you here with some different ways you can connect with me if you have any questions or follow-ups. The link to my website is here, where you can find from the homepage the link to the full tutorial and also the link to these slides. And thank you so much for listening. On the last slide, there's some additional resources if you want to read some more about these topics. These are some papers that I think are good introductions. So
Thank you so much, Emily. I'm just going to chat with you for a little bit while we're waiting to see if any questions come in. Do you remember what year you published this tutorial for the first time?
it was 2018. Yeah.
Okay, 6 years ago. I have to say thank you for publishing it because every time I think about survival analysis, the first thing I do is go to your page and just
Yeah.
remind myself like which way are things supposed to be coded and what's acceptable and like and putting those survival objects together and all the nesting that you do. It's like
Yeah.
you don't remember it. So
I
I'm just so
actually look at my own
grateful.
website quite a bit myself. So especially for things like there are some advanced topics on there, like if you have a time dependent covariate, you have to make a
Mhm.
special format of the data set. I never remember how to do that off the top of my head. So it's a resource for myself as well. But I have changed it quite a bit since then because at the time I wrote it, GT summary wasn't out, GT ServFit wasn't
Mhm.
out. Um, I had shown a lot of comparisons between like base R ways to do things and other like Lubridate package. And in the end, I
Mhm.
decided really, I think there's a better way to do it. And so I took some of that out down the
Okay.
line. So it has evolved over time and it
Yeah.
probably needs another update soon.
I mean, I definitely appreciate the attention also to like the visual displays of the results and the tabling of the results. Because if you've ever kind of dug into the survival objects themselves, those are things that are so hard to extract and get to display nicely. So having those
Yes.
convenience packages and functions is huge.
Yes, they are huge. The functions to make the nice tables of results. I know I used to have my own like little custom functions to even figure out how to get the p-value out of a
Yeah.
log rank test from ServDiff because it's like this complicated nested list and it's actually not that easy to extract it. But there have been some nice, you know, complementary functions in R that have come out since then. So
And I haven't read the tutorial, to be honest. I haven't read the tutorial top to bottom in a while. But I do think what's different about your presentation today compared to the tutorial is that you explicitly talked about some of the pitfalls. Are those in the tutorial or are those only just special nuggets for this presentation?
yeah, I think they're in there, but not
Okay.
as like in defined sections. So the tutorial definitely has a lot more details, and I think some of it might be woven in and some of it might not be. So I should definitely take a look at that and see if I can add that in as well, because I think it's important, especially with some of these kind of mis mistakes isn't the right word for it because some of it
Right.
even comes out of the default way that things come out, like the y-axis not going from 0 to 1. If you don't even know to check for that, it's very easy to overlook it yourself, right?
Yeah. Yeah. So thank you.
So
This
yeah,
is great. There's only praise coming in the chat
okay,
and absolutely no questions.
good. I'm glad that
But
people enjoyed it and hopefully they
yes,
can go back to the tutorial and get more information.
yes. And if you're
Thanks so
still on
much
the
for having
call,
me.
don't forget Emily is chairing RN Medicine and keep your eye on that conference and submit your abstracts.